All right, this chapter is going to focus on different types of chemical reactions and stoichiometry as it pertains particularly to solutions. So before we get into it, we need to define what a solution means. A solution is a homogeneous mixture. So to the naked eye, it just all looks like one liquid. And it contains a solvent and a solute. The solvent is the liquid in which the solute is dissolved. So there is more solvent than solute. There's usually only a tiny amount of solute, and there's much more of the solvent. So in this class, most of the solutions that we're going to talk about are going to be aqueous solutions. So as the name suggests, in aqueous solutions, the solvent is water. So let's focus now on what makes water such a great solvent. In fact, water is referred to as a common solvent, and there are certain aspects of its molecular structure that makes it an extraordinarily good solvent. We know that if we draw the Lewis structure for water, it has a bent geometry because these two lone pairs occupy space, and that makes a bent geometry where the bond angle here is just under 105 degrees. There's a nice strong covalent bond between oxygen and hydrogen. Okay, so these are good covalent bonds, but the electrons in these bonds are not shared equally between the O and the H. And the reason for that is that oxygen is very electronegative. Oxygen is the second most electronegative element on the periodic table. And hydrogen is very electropositive. So that means that when we have hydrogen and oxygen bonded to each other, oxygen is going to suck most of the electron density towards itself. Okay, so there's a very unequal electron density distribution in that bond. Another way of saying that is that it's a very polar bond. Okay, and that means that because of the asymmetry of the molecule, water is going to be a very polar molecule. So we can draw partial charges to show the polarity in the molecule. We can draw bond dipoles, kind of pointing towards that more electronegative element. So there's a very up towards the oxygen. So this is a very polar molecule due to its polar bonds and its asymmetry, its bent structure. And its polarity is what makes it such a good solvent, okay? The polarity is the basis for dissolving polar compounds like salts, ionic compounds, and even non-ionic compounds like sugar, for instance. Anything that has polarity is going to be easily dissolved in water. Okay, so the polarity is what makes water such a good solvent. And it's often called the universal solvent. It's a bit of a misnomer because not everything dissolves in water. Okay, you can just think about oil, for example. Oil doesn't dissolve in water, but lots of compounds, any polar compound is going to be eager to dissolve in water. So let's take as an example salts. Salts are ionic compounds. That means that they contain cations and anions. And cations and anions have charges on them, positive and negative charges. So let's just take the classic iconic salt, sodium chloride, or table salt. If we take table salt, which is a solid, and put it in water, I'm going to put water over the arrow. A lot of times you'll see the solvent over the arrow. Then that salt will break apart into its component ions, which will become dissolved in the water. So these little aqueous labels mean that those ions are dissolved in water. And it's just kind of separating it from the regular solid, liquid, and gas phase. So aqueous means dissolved in water. Okay, this is such a common thing that we have its own specification. when we write chemical reactions for aqueous level, what that looks like is you have the positively charged sodium ion, and you have your very polar solvent molecules, which kind of cluster around that sodium, and they cage it. So I'm going to draw what that might look like. Oops, I'm losing my my picture here. Basically, the more electronegative end, the oxygen, is going to orient itself towards the cation. So the water molecules will form this very nice arrangement around the sodium cations that is a very stable arrangement. Okay, so what I've drawn here is that we have the electronegative oxygen end of the water molecules orienting themselves around the sodium ion. Chloride is an anion, so it is going to be surrounded by the more electropositive end of water, the hydrogen atoms. So we're going to have kind of an opposite effect, but it still is very, very favorable. Now, there are more molecules probably than this around. I'm just drawing this as kind of a cartoon. So this cage around the chloride anion is also very stabilizing to that anion. So what we have is a driving force towards the dissolution of these compounds, where the solvent molecules, ions, produce these very favorable interactions that are the reason why salts dissolve so easily in water.